Hi everyone, it's a great honor for me to receive the award. I would like to first thank my PhD advisor Sven Koenig for his encouragement, support, and guidance through this journey. The title of my dissertation is Target Assignment and Path Planning for Navigation Tasks with Teams of Agents. At the early stage of my PhD, I got interested in systems where multiple agents are operating in a constrained environment. What I'm showing here are the automated fulfillment centers by logistic companies such as Amazon and Alibaba. Imagine that if you order a teddy bear online, the system then assigns a robot and plans a path for the robot to carry a shelf that contains the teddy bear from its storage location to the packing station that needs the teddy bear. A human worker at the packing station will then pack the teddy bear with maybe other products in the order into a box and ship it. The box or the parcel will then be transferred to a sortation center by a conveyor belt. Here in the sortation center, a human worker or a scanning machine at the sorting station scans the delivery address of a parcel and then put it onto a robot. The address will be input to the robot, telling the robot which sorting bin on the floor it should deliver the parcel to. Each bin is associated with a certain postal code. In seconds of computation time, the system needs to assign sorting stations to hundreds of robots for them to obtain parcels for delivery, and plan paths for the robots to the assigned station to get a parcel, and then to the correct sorting bin. Hopefully, at the end of this talk, you will learn about how we can apply some of the insights and techniques from my dissertation to this real-world multi-robot system. This was also the last project I finished at USC, jointly with researchers from Alibaba China Logistics. It turns out that the path planning problem in such applications have been widely studied by AI researchers under the name multi-agent pathfinding, or MAPATH. The problem of MAPATH is to find collision-free paths for multiple agents on a graph. Each agent is given a start vertex and a goal vertex. And at each time step, agents can either wait at its current vertex or move to a neighboring vertex. Agents need to avoid collisions, vertex collisions where two agents attempt to occupy the same vertex at the same time step. Edge collisions where two agents attempt to traverse the same edge in opposite directions at the same time step. The objective is to minimize the mixspan, which is the maximum of the arrival times at goal vertices of all the agents. And MAPATH is NP-hard to solve optimally. Please refer to our survey paper for more details. But here, let me tell you more about the algorithm. So here is an example of an optimal MAPATH algorithm called conflict-based search, or CBS. CBS is a two-level algorithm. It plans a path for a single agent on the low level and performs a best-first search on a binary tree on the high level to resolve collisions in the computed path returned by the low level systematically. So the high level does this by imposing spatial temporal constraints. The low level search is an A star in space and time dimensions so that the resulting path satisfies the constraints. I started to think about how we can apply such MAPATH algorithms and techniques to applications, for example, the automated warehouse systems. And I tried to tackle some other aspects of the problems in these applications, which have not yet been addressed by state-of-the-art MAPATH research. This includes target assignment and long-term operations. To do so, I need to address three central questions, namely, how hard is it to jointly assign targets to and plan paths for teams of agents? And how well can one do so? And how do teams of agents execute their computed solutions? My dissertation answers these questions by studying new problem formulations as variants of MAPATH, developing new insights and algorithms for solving both the one-shot and the long-term combined target assignment and path planning problems, and demonstrating their potential for real-world applications. Let's first talk about the one-shot problem. The first observation about the fulfillment center is that there are multiple teams of agents at any time. For example, for team 0, we need to assign shelves to and plan collision-free paths for agents without a shelf. For agent 1, we need to assign spots of the incoming queue into packing station 1 to those agents that are carrying shelves which contain products for packing station 1. So those agents are actually delivering shelves to packing station 1, and also we need to plan collision-free paths for them to the stations. There might be team 2 for packing station 2 and team 3 for packing station 3, etc. We formalize this problem as the combined target assignment and pathfinding problem, or TAPF, where each team is given as many goal vertices called targets as there are agents in the team. As long as one agent moves to one target given to its team, and each target is reached by an agent in the same team, then we are fine. So the TAPF problem is to assign targets to and plan paths for the agents so that overall mixspan is minimized. Of course, agents cannot be assigned targets given to other teams. You can quickly figure out that MapF is a special case of TAPF, where each agent is pre-assigned a target, namely it forms a single agent team. In my dissertation, I present an inapproximability result that TAPF with more than one team of agents is NP hard to approximate within any factor less than 4/3 for mixspan minimization. I also present an optimal algorithm for TAPF called conflict-based mean cost flow. It is a 2-level algorithm. On the high level, it performs a CBS search to resolve collisions among different teams, which is an NP-hard problem. On the low level, it replaces the space-time A-star search in the original CBS algorithm with the mean cost max flow algorithm. This is to compute a joint target assignment and pathfinding solution for each team of agents, since TAPF for one team of agents turns out to be a polynomial time solvable problem. This algorithm can compute an optimal solution for over 400 agents in 1 minute in our experiments. And then I start to think about the long-term problem because the agents, after they reach the targets, they cannot just sit there idly. So the agents need to get assigned new tasks. I formalized this problem as multi-agent pickup and delivery, or MAPD, which is a lifelong or long-term generalization of one-shot problems such as MapF and TAPF. So here, a task can enter the system at any time, and which can be characterized by a pickup vertex and a delivery vertex. Agents have to constantly attend to a stream of new tasks, and one agent can execute one task at a time. In order to execute a task, the agent needs to first get to the pickup vertex of the task, where it starts to execute the task. And then it needs to get to the delivery vertex of the task, where it finishes executing the task. At any time, there are 2 types of agents. Free agents are the ones that are not currently executing any tasks. They can be assigned any unexecuted task, and all free agents form one team of agents in the terminology of TAPF. Occupied agents are the ones that are currently executing tasks. They are moving from the pickup vertex to the delivery vertex of the task. An occupied agent must finish executing its current task before it can be assigned any new task. And it forms a single agent team since it has a pre-assigned target, namely the delivery vertex of the task. In the dissertation, I present some complexity results for service time and mixspan minimization. Service time is the average time it takes an agent to finish each task. And I also present 2 types of online MAPD algorithms. First, decoupled, which assigns a task to and plan collision-free paths for one agent at a time. It is very fast and it has good scalability and can be easily extended to a fully distributed setting. Secondly, centralized, which assigns tasks to and plan collision-free paths for multiple agents at a time. It has good solution quality. Theoretically, I proved that all online MAPD algorithms I presented are complete in the sense of what we call robust for well-formed instances. And well-formed instances are a realistic subset of instances that are true for warehouses and many other environments, which requires that the given graph needs to satisfy some connectivity properties. And empirically, I analyzed the trade-off between better solutions and faster runtime for these MAPD algorithms. And eventually, I started to think about the problem that the robots need to safely execute the plans that are output by our algorithms. In the earlier stage of my PhD, together with my robotics colleague, Wolfgang Honig, we have developed a polynomial time post-processing method called MapPath-Post based on solving a simple temporal problem. The method can take some of the important kinematic constraints into account and ensure safe execution on real robots. And MapPath-Post is part of Wolfgang's dissertation and not a contribution of my own dissertation. But what we found out later is that MapPath-Post works very well for one-shot problems, including TAPF, but not quite well for long-term problems such as MapD. The main problem is that a MapD plan is often too long, and it could take hours for MapPath-Post to compile a solution for a MapD plan, even though MapPath-Post runs in polynomial time. Also, such a post-processing method is not ideal in an online setting. So the last contribution of my dissertation is an improved version of the MapD algorithm, decoupled. It uses a version of A-star search that can work with continuous time to plan paths for single agents and uses a novel advanced data structure to store the computed paths, which allows for efficient operations such as inserting and deleting paths and collision checking that are frequently required in an online setting, such as in MapD. A great benefit of this single agent path planning algorithm is that during planning, the algorithm can consider kinematic constraints such as velocity limits of the robots, and it can work with non-uniform edge lengths. It can also provide a guaranteed safety distance between robots. So here is the demonstration of improved decoupled in a robot simulator. All robots can safely execute the solution, even though there are unmodeled motion and sensing noises and higher order dynamic constraints that are not considered during our planning phase. And we've also further tested the algorithm on a large size instance. Here, the total planning time is roughly less than 10 seconds for the operation that is longer than 30 minutes, which involves up to 2,000 tasks and 250 agents. So this is much more efficient and effective than using discrete MapD algorithms that are then followed by MapPath-Post, because MapPath-Post alone could take hours to post-process the discrete plan for this instance. To summarize, my dissertation makes the following contributions to push MapPath research one step further towards real-world applications. And my dissertation presents new complexity results for different MapPath variants that couple target assignment and path planning together, and also presents new algorithms for this new variants of MapPath. And eventually, I also improve one of the algorithms so that the robots can safely execute MapD plan. Finally, I will give you some examples of how you might use some of the insights from my dissertation for your own research. Here is an example where the information of the future tasks are known. Then we can optimize the order in which the agents execute the tasks. We solve the task assignment and scheduling problem in MapD as a special version of TSP, traveling salesman problem, and compute a TSP tool with small mixed-band that specifies a sequence of tasks for each agent. So this results in a family of improved centralized offline MapD algorithms that are more effective and efficient than the online ones. The other direction is to consider real-world applications such as the sortation center. Here, we formalize the problem as a version of MapD that consists of TAPF subproblems for robots to obtain a parcel for delivery, and MapPath subproblems for robots that are delivering a parcel. Together with colleagues from Alibaba Cainiao, we tested our algorithm in an industrial simulator using real-world data and managed to improve throughput by up to 12% over the baseline algorithm with respect to number of parcels obtained by a robot per second. So this year at ICAPS, I also have two related papers that are related to MapPath. The first one, we studied the effectiveness of online algorithms. And the second one is an application of MapPath algorithms to railway planning and scheduling. Hopefully you can learn more about how we use planning and search to build all learning-based approaches in the machine learning conference for that paper. So please feel free to talk to me in Gather or through email if you are interested in my research. That's all about my dissertation. Again, I would like to thank my advisor, Sven Kornick, and other committee members, my co-authors who have made a significant contribution to my dissertation, and all the MapPath researchers. Most importantly, I would like to thank the collegial ICAPS community and eventually financial support from different sources. Thank you.